So the idea, right, is we have some samples, xi, yi, I equals 1 through n, that are IID from some joint distribution, which we don't know, right? And we're thinking of xy as living in some x by y space, which usually, this guy is a subset of RD, and this guy is a subset of the reals. Right, so our goal is to, predict y given x via some function that we estimate on our data set, right? So what we talked about last time was just kind of like the framework for setting up this problem. So I'll just kind of refresh and then pick up where we left off. Okay, so generally, how do we want to come up with some estimator. In order to do this, we need a way to compare estimators. So, generally we think about prediction performance in terms of risk, right? So prediction performance, of any given function from our input space to our output space, right, measured via a risk, which is basically just the expected value of some loss function, right? So we'll say that the risk of our estimator G is the expected value, where this is over kind of the new data, right, xy, of some loss between y and, g of x, right? And, what we said last time, right, we gave some sort of justification for this, but, the loss is almost always a squared loss or L2 loss, so this gives rise to, a risk of G, that's y minus G of x squared. Right, so this will be the risk that we're most interested in, right? And one of the results we proved was that when we have the L2 risk, right, so recall for this risk function that we've selected, right, we know that the regression function minimizes the risk, right? So inf G of the risk of G is equal to expected value of y minus f of x, where f of x is this conditional mean estimator. Right. Okay. Right, and then the last kind of result that we showed was that, for any estimator, Fn hat, we can, kind of decompose its risk into kind of an estimation error piece and then like a systematic piece that we can't really do anything with, right? So there was, this part that's depends on this regression function, right? And then a piece between the estimator and the regression function. Right, so in particular, this is the estimation error, right? And right, in general, this is why we say we're estimating a regression function, because, this just sits there. This is like the variance of the noise and some, for most models, right? But this is something that might actually go to zero is ingrows. So this is the object we focus on. Okay, so now the question is kind of how do we actually find our estimator f in hat, right? And so by far the most common thing to do is some form of empirical risk minimization. And so all that means is kind of, you know, I want to sort of minimize this risk. I don't know what this is equal to because I don't know the joint distribution of x and y, but I have my data, so I just kind of replace like the expectation with, you know, an empirical average, right? So this is, you know, the basis of sort of, you know, how we fit like linear models, like least squares regression, and also how we fit like neural networks and these sorts of things as well, right? So right, there's you know, nothing sort of magic or complicated about this idea. I mean, the basic idea, right, is it's, you know, common and stats to estimate, you know, unknown, you know, expected values. Right, with known empirical averages. Right, and so, I mean, there's many examples, right? Like the sample mean estimates the population mean, the sample variance estimates the population variance. And in general, the way that, you know, we fit kind of regression functions is this same idea, right? So, you know, we estimate the risk. Via, you know, its empirical version, right? So, you know, I'll just put an N on it to indicate that this is the empirical version. Right, so this is the empirical risk. Right, and if I want to kind of minimize this with respect to g, right, there's like kind of nothing stopping me from just, you know, doing the same thing sort of over here, right? So in particular, something like this is then estimated by, you know, right, just optimizing the empirical risk, right? So in general, right, you know, this is called empirical risk minimization, and, you know, this is what we do kind of all the time. Right, so there's an issue with this, right, which is the fact that, you know, sort of if we're going to minimize this guy over functions g, then, you know, this is always something that's positive. So any function that exactly interpolates my data points is going to minimize it, right? So, you know, above is minimized for any g such that, you know, yi equals g xi, right, for all I, right? And this is undesirable, right? You know, if you can imagine a situation where, you know, let's say our regression function, you know, our data is like y equals x squared plus noise, you know, we're going to have data points that are like this, maybe, right? And so if I just minimize the empirical risk, then, my solution's going to be something like, I don't know, that, right? And so if we're thinking about prediction, right, I get a new data point, maybe here, then I'm not going to fit it well, right? What we'd like is something that fits just kind of sort of a smooth version, right? So in some sense, right, this is the same thing as we talked about in the beginning, right? What we want to do is kind of enforce some like low-dimensional structure in order to, kind of not, overfit to the data is how we would, the jargony way of kind of saying this, right? So, if we're going to fit a regression function, we still want to do this, empirical risk minimization, but we need to, make sure it avoids doing something kind of nutty like this. So, generally, to overcome this, we kind of enforce some lower dimensional structure on our sort of estimated functions, right? So on the kinds of G's that we're allowed. And usually, this is leveraging perhaps some prior knowledge about the regression function, or, making some sort of trade-off between, a complicated function and something that'll fit better. So, this is kind of done by, sort of in two ways, right? So, okay, so what do? We, leverage prior knowledge of the regression function, right? Perhaps you know that it should be linear for some reason, or assumed low-dim structure. Right, so kind of the idea is instead of, looking over all possible functions G, right, we might assume that our regression function lies in some set G, right, where, G is a class of I don't know, perhaps like linear functions, right? It's pretty common. If you actually want to do inference and like kind of learn something about the science or the state of the world, you use a kind of simple class so that you can make conclusions about what you've learned. Maybe you would choose smooth functions, right? Maybe you have a lot of data in a big computer and you would choose a neural network, right? Right, so smooth functions could be those with like L2, norm of the, second derivative bounded, say. Okay, right, and so, what do we do, right? Well, the idea is we are going to incorporate this into the ERM, right? So you incorporate into the ERM, either like with a constraint, right? So I might say something like, I want to min G, but only those in this class of my empirical risk, right? Or with a penalty, right, which, I still can consider all possible G, but now I'm minimizing, the risk that is kind of like a data fit term plus, a penalty term, right, that somehow penalizes complicated G's, right, or also is pretty common if you use both, right, so you minimize G in some restricted function class, and you minimize the risk plus the penalty. All right, so generally, like, the penalty term is kind of a way to, like, find a low-dimensional structure in a way that's data-driven, right? You know, generally, right, these schemes are called regularization, right? And it's this is kind of quite common in high-dimensional statistics, right? This is basically how we fit most of our models. Okay, so what I wanted to do now is just to look at kind of like the simplest sort of subclass, which is just going to be linear functions. And then we'll prove some things about, you know, to kind of show how if we assume like a lower dimensional structure, we can move into sort of high-dimensional, you know, they'll work for high-dimensional problems, rather. So, okay. All right, so we're going to look at linear models. Okay, so all right, so for the linear model, all I mean is, you know, the following. So I'm going to take my input space to be RD. My class that I'm optimizing over is going to be the class of, you know, linear functions. Right, so, you know, in particular, I'm thinking that this is like, you know, g of x equals x transpose theta for some theta in RD. Right, and if I do ERM over this class, right, the ERM estimator is least squares. Right, and so what is the least squares estimator? Right, this one has a specific name because it's been studied for like 1 million years in statistics. So, you know, this Fn hat of x equals x transpose theta hat n, where, you know, theta hat is just one of the minimizers of this empirical risk. Right. Okay. So, you know, what we're going to do is assume also a linear model. By which I mean my data was actually, you know, drawn from, you know, such a relationship. So I'm going to assume that my actual regression function, you know, is x transpose theta star for some theta star, you know. For example, you know, I might have y equals x transpose theta star plus noise. Right. And in this case, right, as I mentioned, often the literature will put bounds on, like, you know, the discrepancy between, like, your estimator theta n hat and theta star instead of, you know, directly on x transpose those values. But that's kind of a small point. Okay, so I want to make like one quick remark, right? So, you know, so we'll work, you know, okay, for like the rest of class, we're going to assume like this linear model, right? So we're going to assume that the data was actually generated, you know, in this linear way, right? But I think when you actually use these methods in practice, right? You're usually not really imagining that the data was, created by some neural network or by some linear model, right? In general, you believe that your models are wrong. So kind of the idea, right, is that more realistically, you're kind of like one only assumes this regression function is well approximated by, a linear function or whatever your subclass G is, right? Well approximated by a function in G, right? So in this case, you would call this like a misspecified model, right? And in some sense, like, we kind of think like every model is misspecified because, the world is sort of like more complicated than what we can figure out with statistics. But, okay, but like why does studying like, the linear model and the results given by it still make sense? So, kind of, okay, if this is the case, right, then sort of the idea is, there's no hope that like our estimation error, fn hat minus f of x, goes to 0 as n goes to infinity if we're misspecified, right? Because what we're saying is this fn is going to come from this subclass of functions g, right, which we don't believe f to live in, so there's no way this goes to 0. But, kind of like an easy decomposition gives that, this estimation error is now equal to a sort of systematic error. Sorry, let's do it this way. Let's call this f bar x minus f of x squared plus fn hat x minus x squared, right? So this is a decomposition where by f bar, right, where f bar projects f onto g, right? So kind of the idea, right, is that, okay, so this is something that might, can go to 0 as n grows, right? And this is something that's kind of a systematic error with my model, right? But like kind of the idea, right, is, if you choose, G in a smart way, right, then in some sense you want that the class of functions that you're considering approximates all functions well, right? And so these are sort of like classic results, like, like universal approximation of neural networks and these sorts of things that say, if this class G is rich enough, then, so long as you're willing to make like some assumptions about the smoothness of the underlying function, then, this will be small relative to like the kind of size of the class. So kind of the idea, right, is that in the background, we're imagining this is kind of taking place. When we consider G, we're considering it's a class that's rich enough such that the systematic error is small, but at the same time not so rich that we can't estimate it. So also kind of thinking in this way can help you kind of choose the class of functions G you consider, because there's sort of a trade-off, right? If it's very rich, then you're going to do good approximating all functions, but you'll have a hard time estimating it on the other hand, right, if it's too simple, you can estimate it well, but it won't match the true function, right? So, okay, right, so kind of what we're doing, right, is we're going to study in some sense like this error, right? We're going to assume, you know, the model has generated the, you know, we're going to assume like the function class that we're using matches the way the data was generated, and look at how well we can estimate under that assumption. Okay. And in some sense, too, even like linear, like the class of linear functions is like a pretty good approximator when the dimension and the size of the problem is big. So, you know, you lose some richness, but it's you know, we're not considering a problem that's totally nuts. Okay. So, all right, so when we look at this least squares estimator, the guarantees take the following form. So, all right, so we're doing ERM with the class of linear functions. And what can be proved is the following. So, all right, if we look at, you know, the expected estimation error, so now I'm averaging over the data too, right, of fn hat x minus f of x squared, right, which in this case, you know, I'm assuming a linear model, and I'm assuming a least squares estimator, so this is just x transpose theta n minus theta star squared. All right, and what can be shown is that this is upper bounded by some constant times d over n, right? Where again, d is like the dimension of my input, and n is n's my number of data points, and this is just some positive constant, right? And so this is like, you know, with some assumptions on the marginal of x. Okay, and so we'll prove a kind of version of this in a few minutes. But kind of what I wanted to talk about, right, is you know, okay, so what does this tell us if we're like in high dimensions, right? And essentially, like the result, right, is that this sort of bound, right, is completely uninformative if d's growing sort of more quickly than n, right? Or even at some level if it's of the same order as n. All right, so this is uninformative if d growing more quickly than n, right? So the question might be, you know, is this the optimal bound, right? So, you know, the question, of course, is this the correct dependence on m and n? D and n, sorry. Right, so you might say like, okay, well maybe if I, you know, have a better estimator, then I could improve this side to like log d over n or something similar. Or maybe if I had a better proof technique, I could kill the d altogether, right? But you know, what can be shown, right, is that essentially this bound is optimal for least squares in this kind of general situation. So, you know, what one can show is the following, right? So if you consider any estimator, f tilde, there exists a regression function, right? So there exists kind of a truth such that, you know, this error is going to be upper bounded by sort of the same order term, right? Such that the expected value of the data, expected value x of f tilde n of x minus f of x squared is going to be bigger than or equal to some constant times d over n. Right, so you know, what this means is, like, in a sense, this bound is optimal, right? So you know, kind of the conclusion, right, is that for like high dimensional problems, this sort of least squares is like effectively useless, right? You get kind of errors always. Okay, so then, like, the question, right, is how do we get around this? And of course, like, the idea is that we're going to have to add, like, kind of more structure or more assumptions, right? I'll mention, so we'll prove a version of this result. I'm not going to show you guys a version of this result, but it's these proofs are pretty, like, pretty cool, actually. So they're related in some sense to, like, the LDA example we looked at, like, the first day. Like, the way that you show something for any estimator is, you know, kind of showing that if you have, like, two like, you know, with the LDA, it was like the whole thing is we have these two distributions, and if the two means are too close together, we can never distinguish. And that's, in spirit, the same idea as how you do these kind of converse proofs, which, you know, they're pretty fun if you're into that kind of thing. Fano's inequality, you know, stuff like this. It's some cute results. Okay, so, right, so the question is, okay, now, like, what we've looked at, right, linear model, least squares estimator, right? There's kind of nothing we can do if d is growing with n, right? And so then the question is, like, okay, so, like, what do we do, right? And it's obvious, you know, the whole like name of the game, right, is we assume some additional structure, and you know, by far the most, like, common structure, you know, like that high dimensional statisticians like is this notion of sparsity, right? And so the idea here is that if we assume sparsity, we're going to assume sparsity in you know, in these coefficient vectors, right? So by sparsity, right, I just mean that only a small number of the elements are non-zero, right? So we'll say a vector theta nRD is k-sparse, right? For k is just an integer n0 through d, right? If it has at most k non-zeros. Right, and so usually, or you know, often this is kind of represented through an L0 norm, right, which just sums over the elements and counts the number that are non-zero, right? This isn't actually a norm, but usually it's, you know, referred to as like an L0 norm. Okay, and so so why is this like the kind of low dimensional structure that we like, right? Well, okay, if you think about actually like what we're doing, okay, in statistics, what we're doing when we do linear regression, right, is we want to predict, you know, something about the individuals in our data set, right? So maybe that something is like the presence of a disease or some sort of health outcome, and then, you know, what we have is a bunch of data, you know, that the hospitals have given us about these individuals, right? And so, you know, what are we assuming when we do like least squares regression? Well, okay, there's an assumption that, you know, these features in our data set, this information about the individual relates linearly to the output. And then when we assume sparsity, what we're saying is that, like, okay, well, probably some of the information we have doesn't actually matter in predicting the disease, right? And kind of like, you know, I think in modern data sets, this is often true, right? We are like rich with data now for the most part, right? So it's like, what we do is kind of just use all of it in order to try to predict or do whatever we want to do. And so there is some reasonable assumption that, you know, parts of the data might not matter at all, and that can be captured by the sparsity. It also does seem to be like a kind of naturally occurring phenomenon. So like often, even if you're not like sparse, you know, in your data directly, usually there's some basis that you can transform the data into where you are sparse. So even things like natural images, right, we can change the basis, and, you know, they're usually sparse in some other basis. There's only a few kind of characteristics of the image that are relevant. So, you know, that's a pitch for sparsity. You know, of course, there are other ways that you might like assume structure on, for example, the vector theta, right? You could assume it's monotonic, right? That, you know, the top elements are bigger than the smaller elements, and sometimes this makes sense in some like physics problems. You could assume that it's smooth, right? So elements that are nearby should have similar values. You might assume it's piecewise constant or these sorts of things. And often, you know, the physical sciences, like those sorts of assumptions sometimes make sense, right? Okay, so why did I bring up sparsity, right? Well, we're going to show that in the case of sparsity, you know, these bounds on our estimation error can be improved, right? So the basic idea is the following. Okay, so if we look at the set of k-sparse vectors in RD, right, then this, like, it lives in, you know, lives in the union of, you know, sum j equals 0 through k, d choose j, linear subspaces. Right? All I'm saying is that if I want vectors with k or fewer non-zeros, right, then I've got to consider all of the vectors that have k non-zeros. There's d choose k. All of the vectors with k minus 1 non-zeros, there's d choose k minus 1, yada, 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 right? Okay, so if we knew, you know, theta star lived in one of these subspaces, then, you know, then I would just search over that lower dimensional space, right? So in that case, I would take, you know, this sort of result, right? So expected value data, expected value x of fn hat x minus f of x squared, right? And instead of being less than, you know, a constant d over n, right, this is going to be less than, you know, a constant k over n. And that's great. Now, even if D is growing, so long as K is not growing quite so fast, we have a reasonable sort of bound there. Okay, but we don't know which subspace this lives in, so we have to pay some sort of price for, we first have to find, the lower dimensional space, and then we have to fit kind of in that space, right? And it turns out that the price we pay for not knowing is only a log term in D, right? So kind of the result that we get is the following, right? So because we don't know the subspace theta star lives in, we pay a price. But the price is only a log term. So in particular, the bound becomes, now we're less than or equal to some constant. It's log, of this guy, the number of subspaces we have to consider. Right, but this we can, we can approximate these guys and get that this is, like C, K, log ED over K over N, right? So in particular, right, this is what we know. This is what we get if we knew the lower dimensional space. Now kind of, we have an additional term here, but it's only log in the dimension, right? Okay. Right, so this saves us because now we still have something that is a reasonable bound even if D is growing within, so long as it's not growing. You now have a relationship between the sparsity, the dimension, and the sample size where you can get reasonable bounds. Okay, so for the rest of the class, what I want to do is I'm going to prove this result, and then we're going to make some assumptions about the structure of theta in order to kind of show how that helps us improve these bounds. Okay, so I'm going to make some additional assumptions that make our lives easier for this proof. So we're going to, in particular, consider a Subgaussian linear model. By which I just mean now I've assumed that the noise, has tails like a Gaussian distribution, right? So my data Y is generated, through a linear regression function plus noise, where this noise is Subgaussian. So in particular, I'm thinking epsilon I is Subgaussian with variance proxy sigma squared. Okay, I'm assuming that everybody knows what Subgaussian means, right? It basically it's some control over the tails of the distribution. It allows us to, make statements about the way that these random variables, means of these random variables concentrate. It also lets us, have control over the moments and these sorts of things, right? Okay, so in particular, I can write, sort of a summary of my data as, y equals x transpose theta star plus epsilon, right, where now I'm thinking of these guys as vectors, right? So in particular, like this is an n by d matrix where I've put like all of my xi's, right? This is d by 1, this is n by 1, this is n by 1, right? Okay. So the other assumption I'm going to make is I'm going to assume that my x's are now deterministic. So we've been thinking of these guys as being random, but it'll make our lives a little bit easier if we think of them as kind of fixed and given, right? And so this isn't like a huge, change in some sense because, it's like we can think of them as just being like draws from a random distribution, but there's a little bit of a philosophical distance in the sense that, I now need to look at like a slightly different version of this sort of error metric because there's no notion of like a marginal distribution of x, right? So we're going to assume fixed design. By which I just mean, right, that, in other words, x1 through xn deterministic. Right, so our goal then is sort of to estimate f only at the points fx1, fxn, right? Because there's no sort of like, if there's an x new, it doesn't have a marginal distribution like in the same sense, right? Kind of, again, like given noisy observations. So then, the notion of performance has shifted a little bit, right? Instead of averaging over a new x, we're going to consider the mean squared error. Right, where we say that the mean squared error of an estimator fn hat is just, the sum of the deviations. Fn hat xi minus f of xi squared, right? Mean squared error, right? And so in our linear model case, of course, this is I equals 1 to n of xi transpose theta n minus theta star. Okay, right, so, and again, this is the using the least squares estimator. So this is theta hat n equals, we'll say n arg min theta y minus x transpose theta squared. Right, where now I've just used our kind of matrix notation. Okay. So the first result is just that in this case we can characterize theta n hat directly, right? And it's not hard if you just look at the you take the gradient of that 2 norm and set it equal to 0 and solve. This gives you the characterization. Right, okay, so lemma, right, is just, so if I call mu hat ls equal to x theta hat ls, you know, this is going to be an R in, and this satisfies the following, right? So this satisfies x transpose mu hat ls equals x transpose y. And in particular, then we can characterize theta hat ls as x transpose x pseudo inverse or inverse x transpose y, right? Okay, so, you know, proof is just solve gradient of y minus x transpose theta squared equals 0. Okay, so then the first thing we actually want to prove is the result about, you know, least squares under no assumptions on theta, right? So this is the d over n upper bound. All right, so what I want to show is that 1 over n, if I take the expected value of x transpose theta hat ls minus theta star d squared, right? This is upper bounded by constant times sigma squared r over n, where R is the rank of x transpose x. Okay, so, right, so I have a random, you know, I'm taking an expectation here because this guy is random, right, where the randomness comes from, like, the noise, right? This is the, you know, they use the y's in here, so they have the Subgaussians. Right, this is the variance proxy of the noise. Right, and R is some value less than or equal to D, right? Okay, so let's prove this. Okay, so so the first thing is by definition, if I look at, you know, y minus x transpose theta hat least squares, okay, the norm of this guy is less than or equal to y minus x transpose theta star squared, right? So theta star is my truth. This is my estimated one. This guy minimizes this thing, so it's, you know, it's a bound, right? But, you know, from my assumption on the model, right, that's just going to be the norm of the epsilons. Okay. Moreover, I can get another bound on this same term. So if I look at y minus x transpose theta hat ls squared. All right. Now I'm just going to write out y under my assumption of the model, right? So this is x transpose theta star plus epsilon minus x transpose theta hat ls squared. Right, and now I'm just going to expand this, right? So this is x transpose theta star minus theta hat ls. Okay. I think maybe, I see. Sorry, I was putting the way I've defined this, I don't think I want the transpose here. So I'm thinking of this as having already as, this is like x1 transpose, xn transpose. Sorry. Screwed up my matrix notation. Yeah, I think this is right. Okay. Okay. All right, so now, right, okay. I have two sort of, you know, I can put these together, right? And basically what this tells me is if I look at this object, x theta star, oh man, I really screwed this up, sorry. Let's do it. Theta star minus theta hat ls, theta star minus theta hat ls. Okay. Okay, so then this term, right, minus theta hat ls squared is going to be less than or equal to 2 epsilon transpose x theta star minus theta hat ls. Okay, and so now what I'm going to do is just write this kind of so that, you know, so this is a vector with length n, and so I'm going to write this such that this is a self-normalized vector. So this is going to be equal to 2 times the norm of that guy times, okay, epsilon transpose x theta star minus theta hat ls over x. Okay. Right, so, okay, so this is the object I want to control, right? So this is the thing I have the bound on over here, right? So when I look at this right-hand side, kind of the issue, right, is that essentially this is the object that I need some sort of control over. And the idea is that, you know, directly trying to do this is a little bit hard because, you know, there's a dependence between this vector of my noise, right, and my least squares estimator that was constructed, you know, depending on that noise. Right, so kind of the way that, you know, usual way to do this is to kind of like, in some sense, soup out this vector. So the idea is we'll kind of, you know, now look at a supremum over all kind of vectors in the unit sphere. The only thing is we have to be a little bit careful with, you know, kind of considering the span of the columns of x. So, Okay, so the idea is the following. So I'm going to let capital phi just be an orthonormal basis for my column span, right? So this is like phi 1 through phi r, right? I'm thinking of a matrix in n by r that's an orthonormal basis for, column span of x, right? So in particular, that means, right, that there's, there exists a vector nu, that's a vector in r little r, such that this guy, x theta star minus theta hat ls equals phi times nu, right? Okay, so now kind of the rest of the proof is just rewriting this in terms of, this orthonormal basis, and then using some facts about Subgaussian random variables, right? Okay, so what this means, right, is if I take that term, so this is epsilon transpose x, theta star minus theta hat ls over norm right? Well, okay, this guy, right, and this guy are just phi nu, right, as I just defined. So epsilon transpose phi nu over the norm of phi nu. But this is an orthonormal basis, so I can just erase that guy from the norm, right? And then what I'm going to do is I'm going to represent this as now epsilon tilde transpose nu over norm of nu, which I'll upper bound with, the supremum over vectors and a unit ball epsilon tilde transpose u, right? So here, okay, I've defined epsilon tilde as to just be, this guy, right? This is, phi transpose epsilon. And B2 is unit ball in R. Okay, so kind of the idea, right, is that, this guy is still Subgaussian, right? So we've taken a vector of Subgaussians, kind of, hit it with this orthonormal basis, but you can prove that this remains Subgaussian. So, if you want to prove this, like, bound the moment generating function, right, and you'll get kind of the same sort of bound. So, what I'm thinking, maybe I'll make a note, right? So, okay, so I'm thinking my vector epsilon and Rn is, Subgaussian. I'll put a little n to indicate that this is a vector with variance proxy sigma squared. Okay, and so I guess just by the vector being Subgaussian, I mean it has expectation 0 vector. And if I, take the inner product with any u in the unit sphere, this, one-dimensional thing is Subgaussian. For all u in unit sphere. so these are assumptions I made on, this basically just comes from the fact that individually these guys are Subgaussian, so, they have this kind of vector property, and then you can show that epsilon tilde, my new vector in RR, is, Subgaussian dimension R with the same variance proxy. Okay, so now we're more or less done, right? So, okay, so I'm going to take this, so this is my bound I have so far. I'm basically going to bring this over. And so what we've shown, is the following. So what we've shown is that x theta star minus theta hat ls norm squared is less than or equal to 4 sup u in unit sphere u tilde transpose u squared, right? Right, so I take this guy over, I lose the square, and then I square it again. That's kind of the idea. Okay, I don't know, we can upper bound this for sup u in B2 e tilde squared u squared, right? But of course, this guy, this is always equal to 1. So this is 4 e tilde squared, right? And so what I actually want to bound is 1 over n times the expected value of this, right? So 1 over n, expected value with respect to the noise. So this is 4 over n, sum I equals 1 to r, expected value of e tilde I squared, right? But these guys are Subgaussian, so, this is upper bounded by 16 sigma squared over n, right? So this is just Subgaussian moment bounds. All right, okay. So, sorry, 16. Each of them is bounded by 4 sigma squared, and we have r of them. Right? So, okay. So we proved the result in the general case. What I want to do now is to show how, by just assuming a bit of structure on these thetas, we can improve this bound. So the kind of structure I want to assume is just that now let's assume that this theta star lives in an L1 unit ball. So now let's consider a constrained least squares problem. Okay, so I'm going to assume that my true theta is in the unit ball, right, where this is just, I'm thinking the vectors in RD such that the L1 norm, right, which is the sum of the absolute values, is upper bounded by 1. And so then I'm going to define my least squares estimate over the unit ball as just, now we're not minimizing over all theta and RD, but only those theta with bounded L1 norm. Right, and what I want to do is just kind of look back at this proof and see how this constraint helps us, right? Okay. So now I'm going to go over here and prove the next sort of result. Okay, so, all right, so theorem, okay, I'm going to assume the same, well, all of the same sort of assumptions except one additional one where I'm going to assume a column normalization such that the max column norm of my X matrix is upper bounded by root n. And then what I'm going to show is that if we look at the same expected value of my mean squared error, but now I have my least squares estimate that has bounded L1 norm, now we're going to get that this is less than or equal to constant times sigma squared square root log d over n. So, okay, so now, so just to comment on this bound, right? Okay, now this allows us into like the high dimensional world, right? We can have d growing within, but we're getting a slower decay, right? So now we only have a kind of 1 over root n sort of decay. And so, okay, the proof works almost the same as before, right? So as before, okay, so like nothing I did here, right, depended on what least squares estimator I had, right? So I can use that again, right? So x this is upper bounded by 2 epsilon transpose right? And so now kind of the idea is, again, right, we want to control this guy. The difficulty is the dependence between the least squares estimator and the epsilon. So what I want to do is kind of like soup over these vectors, right? But now I know that both of these guys live in the L1 unit ball, right? So kind of the correct supremum is the following, right? So I'm going to take 2. I'm going to soup over vectors. What notation? Maybe omega in, unit ball minus unit ball. E transpose x omega. Right, where, sort of like unit ball minus unit ball, I just mean, x minus y, where both of these guys are in the unit ball, right? But this is like a symmetric sort of set, so this is just going to be like double the unit ball, right? So this is just 2 B1. Right, so, okay, so this is just equal to 2 sup, or sorry, this is, we're now twice the unit ball, so I can write this as 4 omega and the unit ball E transpose X omega. Okay, so now kind of the idea is like we're going to play like sort of the same game, right? And what we're going to see is that, you know, everything that's happening in here, you know, the error keeps things Subgaussian. And so now instead of like, you know, bounds on the moments, I'm just going to use bounds on kind of a supremum of Subgaussians and polytopes and these sorts of things, right? So kind of the idea is, you know, since, you know, my vector, my noise vector is Subgaussian and n with variance proxy sigma squared, and I've assumed this column normalization such that the 2 norm of my column is less than root n. Then if I look at the inner product of epsilon with any column, this is also Subgaussian, but the variance proxy is grown perhaps by this n. This is Subgaussian. Now n sigma squared. Okay, so then this is just a vector, you know, of these guys, right? And so that vector is also Subgaussian with the same variance proxy, and so kind of using by bounds on max of Subgaussians. What do we get, right? So 1 over n, expected value noise of x theta star minus theta hat b1. Right, so this is less than 4 over n sup omega and the unit ball, O1 unit ball, e tilde omega, right, where e tilde in R d Subgaussian d n sigma squared. Right, and so then this guy we can just bound with okay, square root of the variance proxy times 2 log 2d, which is kind of the number of vertices for the polytope, and you know, we simplify this guy and we get c root c sigma root log d over n. Okay. So, okay, so I'll make 2 comments and just stop for questions. So the first comment is that the whole first proof we did actually applies as well to the least squares estimators and the unit ball, right? So in fact, you can tighten this bound to be actually like min of this one, and d over root n. Sorry, I think I implicitly assumed that R equals D in this case. So we have X transpose X is full rank, right? So you can strengthen this to have the minimum of these 2 guys, right? And then the final comment I want to make is you can kind of redo this same argument, but instead of the L1 unit ball, use the L0 unit ball, right? So you can redo the same argument for like actual k-sparse vectors. It becomes a little bit more technical in some sense, but the bound for k-sparse theta hat and theta star using just, again, the same strategy is, this MSE, expected MSE is upper bounded by sigma squared k over n log ed over k, right? So this is kind of like the argument I made earlier that kind of what you pick up for not knowing the sparse subset is just this this extra log term, right? This is the price you pay for not knowing which subspace you're living in. I'll also kind of mention that, this sort of like actually doing the least squares over the L0 ball, like actually doing the k-sparse least squares is computationally efficient, right? You can prove that, in order to do this, what you have to do is just do least squares over all, d choose k vectors, and so, it becomes like exponentially time-consuming computationally. So, in practice, you kind of get around this. Instead of doing the constraint directly, you kind of penalize in a way that enforces some sort of sparsity, right? And this is the whole idea of the lasso. So, when we were talking about regularization, we said you could optimize over a subclass, right? Or you could penalize. And so, kind of what you do there is you penalize in a way that enforces this sort of sparsity. So, okay, so I think, so I'll stop here and take questions today if there are any, and then on Wednesday we'll move to AMP. And so kind of the idea of AMP is it gives us a way to like at once solve these like penalized ERM problems, and also it's a tool to give theoretical guarantees about things like the mean squared error for like these more complicated estimators. So, okay, I'm done for today. Thanks.